Continuing our study of name reactions, let's investigate another oldie but goodie, the Cannizaro reaction. This reaction involves the disproportionation of two equivalents of a non-enolizable aldehyde, where disproportionation means that one molecule is oxidized and the other is reduced. So as we can see here, two equivalents of the aldehyde will produce one equivalent of the corresponding alcohol and one equivalent of the carboxylic acid. The reaction was discovered by Italian chemist Stanislao Cannizaro at the University of Palermo in Sicily, who published his results in 1853. In its original formulation, two molecules of benzaldehyde react in an aqueous sodium hydroxide solution to yield one molecule of benzoic acid and one of benzyl alcohol. Given that the reaction occurs under strongly basic conditions, the product is actually sodium benzoate, which is water-soluble, and therefore benzyl alcohol, which is neutral, can be separated by extraction into ether. Dilute hydrochloric acid is then used to protonate the benzoate to give benzoic acid. There is an enduring joke among synthetic chemists which says Cannizaro was so poor that he could only afford two chemicals for his lab, sodium hydroxide and benzaldehyde. He mixed them together and thusly discovered his name reaction. Of course, this is indeed just a joke, but the reaction illustrates how empirically and haphazardly organic reactions were discovered back then. The reaction is quite general for aldehydes that cannot enolize. If the aldehyde is enolizable, meaning that it has alpha hydrogens, then enolates tend to form, followed by aldol reactions. The synthetic utility of the reaction is limited because there are better ways to oxidize an aldehyde to a carboxylic acid or reduce it to an alcohol. It is, however, important to be aware of this reactivity when planning reactions of aldehydes under basic conditions, such as with aldol chemistry. For example, when using formaldehyde under basic conditions, a very important side reaction will be its Cannizaro reaction to yield methanol and formic acid, which in many cases can participate in further side reactions. As we will see in a moment, clever applications of the Cannizaro chemistry have been devised, and therefore the reaction also has synthetic significance. The mechanism of the reaction is a bit complex. This is demonstrated by the fact that the rate equation contains two terms. As we can see, the reaction is second order in aldehyde, which confirms that there are two molecules reacting with each other in the rate determining step, but the order in hydroxide ion is somewhere between 1 and 2, revealing a more complex role for the base. Let's see how this works now. Beginning with this generalized aldehyde and under strongly basic conditions, the hydroxide ion attacks the carbonyl to form this species at equilibrium. Under sufficiently basic conditions, this species can be deprotonated to form this dianion, again at equilibrium. Although the main species in solution is the previous one, the dianion is much more reactive, and it is believed that the key step proceeds via this species. The key step is the irreversible expulsion of a hydride from the dianion. The hydride is passed along to a second molecule of neutral aldehyde, forming the corresponding carboxylate and alkoxide. In this way, the aldehyde oxidizes while reducing another molecule. Finally, a water molecule will protonate the alkoxide to give the alcohol. We should note that reaction through to the dianion involves the intervention of two hydroxide ions, which explains why the rate equation is partially second order in hydroxide. Now that we understand the mechanism, let's check out some applications. A Cannizaro reaction may be observed when carrying out crossed aldol reactions. These reactions are very successful when an enolizable substituted aldehyde is reacted with a non-enolizable reactive aldehyde. In this way, a homoaldol reaction cannot occur. Let's take a look at an example of this. If cyclohexyl carboxaldehyde is reacted with formaldehyde under basic conditions, only one enolate can form, because formaldehyde has no alpha hydrogens. At the same time, the enolate of cyclohexyl carboxaldehyde will react preferentially with the much more reactive formaldehyde and not with itself, to yield the crossed aldol product in high yield, which is this compound here. However, now the crossed aldol product is also a non-enolizable aldehyde, given that this alpha carbon is now a quaternary center, so this can be involved in a Cannizaro reaction with formaldehyde or with itself. If the chemist carrying out this procedure is not careful and does not control the reaction, they may end up obtaining only the Cannizaro products. Apart from these situations involving unwanted side products, there are actually quite a few clever synthetic applications of this chemistry. We cannot list them all, but just to give you an idea of what chemists can do with this reaction, consider the following substrate. If a molecule contains two carbonyl groups and yet is not enolizable, as is the case here, one might wonder if it is possible to induce an intramolecular hydride transfer. Remember that the key step in the mechanism involves hydride transfer from one aldehyde to another, and there is no reason why this could not occur with adjacent carbonyls on the same molecule, which in this case would yield mandelic acid. Indeed, this can be done very cleanly, and the hydrogen on the aldehyde group can be transferred onto the ketone carbonyl. We must also notice that the product is racemic, also called paramandelic acid, unlike naturally occurring mandelic acid, which is optically pure. Chemists have been at work to make this reaction enantioselective. To do this, one needs some kind of chiral template to guide the reaction, ideally a catalyst, so as to use only a tiny amount. Also, this catalyst must be very effective to overshadow the uncatalyzed reaction, which would lead to a racemate. This is also quite possible. To illustrate this transformation, we will highlight a study by Xiaoming Feng from Sichuan University in China, published in 2015. This brilliant work highlights several facets of the Cannizaro chemistry. First, it can occur intramolecularly. If the aldehyde hydrogen is isotopically labeled as deuterium, all of it gets transferred to the adjacent ketone. Second, metals catalyze the reaction, and this application is predicated on the ability of iron-3 salts to promote the hydrogen transfer, although a discussion of the exact mechanism is too complex for this tutorial. Given that this is the case, designing a chiral ligand to bind both iron-3 and the substrate has the possibility of inducing enantioselectivity, although obviously not just any ligand will do. It has to be designed properly for maximum enantioselectivity and for its catalytic power. Note that only 1 mole% of the catalyst is used. Third, the hydroxide ion is not needed to trigger the hydrogen transfer. Any strong nucleophilic base will do. In this case, potassium tert butoxide is used, which is even slightly more basic than hydroxide. Attack of this base onto the aldehyde will ultimately lead to an ester of mandelic acid. Obviously, all sorts of new substituted mandelic acids can be made by this methodology as well. This is just one of the many applications of the Cannizaro reaction which creative chemists have been able to invent. In this way, the old chemistry of supposedly destitute Professor Cannizaro is alive and well, almost 170 years since its initial report.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.